Hello, and welcome back to the Cedille Cast. In this video, we explore a very recent result by Abel and Coquand concerning the combination of impredicativity and a strong form of proof-irrelevance for propositional equality. Specifically, this combination of features, which exists in the lean proof assistant and also in Cedille, results in a failure of strong normalization of the type theory. However, this result does not impinge upon logical consistency of either theory. This video will explain each of the terms impredicativity, proof-irrelevance, and strong normalization, and demonstrate in Cedille a similar derivation as given by Abel and Coquand. A link to their paper is given in the video description and in the Cedille code associated with this video. If you have watched previous Cedille casts, you have seen already the use of impredicativity. Generally speaking, a definition of some object or term is said to be impredicative if it involves quantification over some collection which could contain that object. Unrestricted, such quantification can lead to logical inconsistency. The classic example of this was discovered in the early 20th century by Bertrand Russell. Russell's paradox arises from the formation of a set containing all sets which do not contain themselves, and asking whether such a set contains itself. The standard approach to ruling out inconsistency from impredicativity is to forbid impredicativity, often by constructing an infinite universe hierarchy, in which definitions living at level 1 may quantify only over all possible definitions at level 0, and so on. Alternatively, type theories like System F or the calculus of constructions are able to allow impredicative quantification without inconsistency. In the derivation of Abel and Coquand, impredicativity is used in order to type self-application. Let's take a look at two simple examples of self-application, typable in System F. As a first example, consider the identity function. And what happens if we try to apply ID to itself. In the application, the type variable x in the type for all x, x0, x, is instantiated again to the type for all x, x0, x. In Cedille, in selecting an application where a type argument has been instantiated, you can press M to toggle the metavariables buffer. No amount of self-application of the identity function will enable us to define a looping term. Let's consider now a second example, which brings us right upon the precipice of divergence. Call this little omega, whose type is for all x, x0, x, given such an argument, return an expression of the same type. Again, in the application, the type argument x is instantiated to the type of the term itself for all x, x0, x. If we could somehow type omega applied to omega, then we would have a looping term known as capital Omega. But in System F, little omega cannot have the type for all x, x0, x, which would be required in order to apply omega to itself. The reason that it cannot have this type, informally speaking, is that in just looking at the type of the argument, we know that the only terms which inhabit this type are equal to the identity function, which omega is not. In fact, no endlessly looping term can be typed in system F, as it is strongly normalizing. The property of a programming language that no definable terms are looping is known as normalization. If there are multiple ways that a term could be run to produce a value, then a language is called weakly normalizing if there exists some sequence of evaluation steps that results in a value, and strongly normalizing if all possible ways of running the term result in a value. We now turn to proof-irrelevance. There are two different, but closely related, notions of proof-irrelevance. The first, and perhaps most commonly known, is the property of any two proofs of some proposition being equal to each other. A trivial example of this is the proposition true, the trivially true proposition which contains only one element. For those following along at home, consult the Cedille Cast repo to see what your options file should look like if you want to have support for data type declarations. Unique true is the proof that for every t of type true, t is equal to truth. And this is arrived by pattern matching on t, considering the case where t is true, and returning beta, proof of reflexivity. Often, it is especially useful to have some specially designated sort of proof-irrelevant propositions, usually called prop. This is not the case in Cedille, and actually, this notion of proof-irrelevance is not the most comfortable one for Cedille either. As we have seen in previous videos, Cedille supports implicit quantification over terms and types. Implicit is another way of saying computationally irrelevant. So here, we interpret proof-irrelevant as meaning that one need not compute anything in order to make use of the proof. Now, the type true is even more trivially proof-irrelevant in this sense. Consider. Given a proof of true that is erased, we must construct an unerased proof of true. This is trivial. We ignore the erased proof of true and just return triv. Abel and Coquand use a propositional equality type which has associated with it a computation law, making its proof-irrelevance closer to this second sense. Functions defined over such proofs need not even pattern match, need not even do the most trivial form of computation over such proofs. Abel and Coquand use propositional equality between types to define type coercions, enabling self-application of omega above. In Cedille, we do not have a way of expressing propositional equality of types, only between terms. But we can express the notion of a type coercion, and it turns out that type coercions are indeed proof-irrelevant in Cedille. Recall that casts are defined as the dependent intersection of functions f of type a to b with proofs that f is equal to the identity function. Let us now show that having an erased cast between two types is just as good as having one unerased. Given a cast between A and B erased, construct an unerased cast. First argument must be a function from a to b. A lim cast takes some erased cast argument and produces a function from a to b. We give it such a cast, and here's the function. We ask, what does a lim cast erase to? It erases to the identity function. Thus, the entire expression erases and normalizes to x, and this entire expression erases to lambda xx. The proof obligation that the left component of this intersection is equal to the identity function holds by beta. In analogy to the Abel and Coquand paper, Castorel shows that one does not need to inspect or compute with an assumed cast at all. With these preliminaries behind us, derivation itself is quite short. Define the type bot, short for bottom, also called false, to be the type of proofs that everything is true. So no such proof of bot can exist in a sound logic. Define not A to be the type of proofs that A implies bot. And define top to be the type not bot. Now comes the first tricky part. Let us prove the fact that it is not the case that for every two types A and B, there exists a cast from A to B, and call this little omega. Assuming such a cast, we must inhabit bot, which has type for all xx. So we introduce an arbitrary type x and must inhabit it. Our goal will be to coerce some term of type top to the type x, which we can do because we have assumed that a coercion exists between all two types. So one exists between the type top and x. Now it is simply a matter of introducing a term of type top. Top has the type bot implies bot. We could, of course, simply return x, and this would be type correct, but the erasure would not be the one we desire. Instead, we can take the argument x, which has type bot, use impredicativity to instantiate it to the type top. This is necessarily impredicative because top references bot in its definition, and apply x to itself. Finally, we may type capital Omega under an inconsistent context in which we have first assumed the existence of a cast between any two types. It has the same type as little omega. We take little omega, give it the cast C, this now has the type for all XX. We instantiate it to the type top. So we can give it an additional argument of type bot, which is omega C. If we try to normalize this expression, it hangs Cedille. But we can see from just normalizing the parts that the head of this application is lambda x, x applied to x, and is applied to lambda x, x applied to x. Languages with dependent types benefit from the underlying theory being strongly normalizing, as the type checker might be required to determine whether two terms are equal to each other. In the absence of strong normalization, type checking under these circumstances becomes formally undecidable. So, why might some languages decide to forego this feature? One answer is that proof-irrelevance and impredicativity are quite nice features in their own right. Proof objects can be quite large, and manipulating these at runtime carries a performance penalty. The strong form of proof-irrelevance considered here can be very useful for writing proofs, say if the property mentions some type-coerced term. Impredicativity enables complex forms of self-application, useful for deriving recursive combinators. For example, it is used essentially in the derivation of inductive data types in Cedille. Another answer concerns a mixture of both the practical and philosophical. Even in strongly normalizing theories, it's possible to write programs, such as Ackermann's function, which take unreasonably long on reasonably sized inputs, perhaps even longer than the eventual heat death of the universe. If you are asking your type checker to compare two terms, where such an expression occurs within one, the fact that the check will eventually terminate might not mean very much if you wish to have an answer within your lifetime. Now, an example of such a long-running program occurring within a proof rarely occurs unintentionally, and in my experience, the same is true also for looping terms. Regardless, it seems like an interesting decision to explore in the design space of dependently typed programming languages. That's it for this video. Thanks for watching, and see you in the next one.